The idea that the ancient Egyptians needed advanced technology to create extremely flat surfaces is not a new one. The words aircraft precision and CNC-level quality are descriptors often put to the boxes inside the Serapeum at Saqqara. All this talk of precision and flatness in ancient Egypt made me wonder, since perfect machine flat surfaces do not exist in nature, how exactly could ancient people have achieved at least what appears to be a high level of flatness on some of these boxes, and why would other boxes or surfaces they made not have the same level of flatness? This brings us to a fundamental question at the crux between mechanical and archaeological history. How did ancient people make anything flat and smooth when there was no master flat or smooth thing to start with? Go out into the woods yourself with basic tools and try to build a straight edge ruler or a carpenter square. It's going to be hard. Now we need to define a few general ranges of flatness in order to figure out what category these items fall into, because the tools and ways to measure them change as the surface flatness increases. We have two standards by the American Society of Mechanical Engineering. Y14.5 defines flatness tolerance symbols, and B89.3.7 covers flatness measurements using CMMS. I am going to break these standards down to categories with the criteria: what measurement tool is needed to appreciate and measure the flatness, and what method today can achieve that tolerance. In engineering, tolerance is the permissible variation in the size, shape, or position of a manufactured part from its ideal, nominal, design value. In other words, how big or too small are you willing to tolerate before the part becomes unusable? Tolerance is measured as a plus or minus by a certain value off that nominal designed value. When it comes to flatness, we have several different categories. First, we have the rough level. This is a flat surface created by casting, forging, or what is left after being rough sawn. This is the type of flat we would see in general construction and the type we would measure with a straight edge. This would also be the state a cast metal part would be in before being checked with a feeler gauge or surface plate with bluing to see if rough machining is needed before that final precision surfacing. Deviations of 1/10 to 1/50th of an inch, quarter millimeter to 1/4 millimeters are typical. Then we get to machine flatness from a mill, lathe, or surface grinder. Tools used to measure the flatness here would be a surface plate plus dial indicator or height gauge, or laser interferometer for large parts. Tolerances here range from 1 to 5,000th of an inch for general machining. Here, flatness will usually be called out in thousandths of an inch or microns. The final level of flatness that modern society has broadly achieved or defined is precision ground or lapped flatness. Tools used here would be an optical flat and monochromatic light machine or coordinated measuring machine. Tolerances here are in the microns, 1/10,000th of an inch. At this stage, straight edges aren't accurate enough. You're measuring light bands or interferometric fringes. This type of high precision is needed for the making of the measurement equipment itself: gauge blocks, surface plates, mechanical seals, bearing, and then high precision scientific parts, laser and optical settings. It is quite common to use this level of precision, but it isn't achieved for aesthetic reasons. It is needed for a precise scientific or engineering reason. Now, there are many channels that speak of the massive stone boxes at the Serapeum of Saqqara in terms such as impossible precision or aircraft-grade precision. These words are often paired with a graphic showing either a carpenter's square or a straight-edge machinist ruler, or sometimes a laser level of the type people use in general construction. Neither of those three instruments would measure a tolerance or show deviations larger than the rough level. As far as I can tell, no one has used tools such as a surface plate and dial indicator or laser interferometer on those. In ancient Egypt in general, the tightest stone fittings that I can find would be the surviving casing stones on the Pyramid of Khufu. Those joints have a mean width of 0.5 millimeter, but that is joint quality between two faces, not flatness per se. Flinders Petrie did measure the coffers of the Great Pyramids and left some measurements for us to look at. As noted by Petrie, the coffer of Khufu was measured with calipers and an offset from the mean plane. Using these methods, Petrie found there were great irregularities in the workmanship of the coffer. Saw marks and other irregularities were also found. The coffer of Coffer was of much better work, but in all the measuring that Petrie did, he did not measure flatness of the surfaces. Here are the measurements that he did do. As you can see, he measured length, width, volume, and those type of dimensions, but not flatness. So in reality, the only measurements we have of these so-called super precision boxes have been done with tools that cannot measure in anything above the rough flatness levels of precision. Consider, for example, this stone sarcophagus that I have overlaid a laser level beam on. This may seem like a very compelling way to show flatness, and multiple people have done this as a demonstration. But here's what's actually happening. A laser line from a construction laser or a line level projects a plane of light. When you see that plane intersect a surface, you're just checking alignment in space, not how far the surface deviates from true flatness. If you align the laser to graze along the top of a sarcophagus lid, the bright line shows where the surface meets the plane of light. Any dips or humps might appear as shadows or gaps, but only if they're large enough for your eyes or camera to perceive. This is analogous to using a long straight edge and backlighting. You're only seeing regularities beyond a few tenths of a millimeter depending on distance and lighting. To measure a tolerance, or to have one, you need a numerical reference, the nominal geometry, and a measurement method that produces a quantitative deviation from that value in inches or millimeters. And you have to have a known instrument accuracy. A laser line alone gives you none of those. You're just eyeballing coincidence between those two visible edges and no way to read out the deviation. Remember, the process of machining something flatter and flatter through those various stages is logarithmic. Let's use those Khufu casing stones as an example, as they are the most precise joints I could find that have actual measurement data, even though we're not talking about flatness here. What you're actually looking at is a comparison of precision, a scale showing how closely different kinds of surfaces fit or align, from the roughest masonry all the way to the most exact lapped optical surfaces used in modern technology. At the far left, you see the broad tolerance range of rough stonework, gaps of several millimeters, the kind you expect to see from ordinary hand-cut blocks or rough-dressed ancient walls. Next comes the machined range, where tolerances drop below a millimeter. This is the realm of finely planed metal surfaces, where in the case of ancient Egypt, the incredibly tight joints between the Great Pyramid's casing stones, which Flinders Petrie measured at around half a millimeter wide. That's fantastic for that time. Yet this level of accuracy was achieved thousands of years ago, using a clever method I will explain in a bit, and no, they didn't use a pounding stone to get them that flat. Moving to the right, we enter the territory of ground surfaces, parts finished on modern surface grinders with flatness measured in hundredths of a millimeter. Finally, at the far edge of the scale, we reach lapped precision, the mirror-like perfection of optical flats and gauge blocks where surfaces are so accurate they stick together by molecular attraction. Here tolerances are down in the realm of microns and nanometers, thousands of times finer than anything visible to the naked eye. So when we are talking about pyramid casing stones being fitted within half a millimeter, we're not saying they are machine perfect or lapped, but what we are saying is that for architectural stonework, massive blocks weighing tons, this was astonishing craftsmanship, well into what engineers today recognize as the machined precision range. Remember, we are talking about joint accuracy though, and not flatness over a large plane. At this point, I can hear everyone shouting at their screens. But you forgot the amazing coffer at El Lahoun, the pyramid of Senusret II. Sure, it's slanted a bit, but the parts that aren't slanted must be aircraft precision straight. You can't explain that, man. It's totally impossible to do back then. Well, I can assure you that I have not forgotten it, and we are about to go over its features in a close manner. But before we can make any conclusions, we must have data. To paraphrase the words of my favorite childhood hero, Sherlock Holmes, if we do not start with data, we will find ourselves bending facts to fit theories instead of theories to fit facts. I myself want to fall into the latter camp, where any theory I present must fit nicely around the cold, hard, and immovable facts as we find them. This is the sarcophagus in question, and we have some excellent numbers and measurements for it, but we must understand what they are numbers and measurements for. We will focus on the main sarcophagus with the broad brim, although there are two others as well at this location. Flinders Petrie did some excellent work here, and while he did not have modern measurement tools and could not have used the absolutely most accurate methods we have today, his data is very good, and as far as I can tell, is all we have. The two main measurements we will focus on for this video will be straightness of the edges and planarity. Let me be very clear. Straightness, once again, is not the same as flatness across a full plane. Petrie established a straight reference using a straight edge ruler and then measured how much the edge deviated up or down from that straight edge. The second thing Petrie measured was planarity, that is, how much an item does or does not adhere to a flat plane. The subject of planarity gets very complicated very quickly, but for the purposes of this video, we are speaking about measurements of any concave or convex deviation from a true plane. Petrie found the following measurements for edge straightness. As you can see in this table here, what we are seeing is Petrie's measuring of edge straightness down to a few thousandths of an inch. Face curvature is limited to only a couple thousandths of an inch across that surface. That is astonishingly tight for hard stone over sarcophagus scale lengths and very good workmanship. But where does this fall within our previously established tiers of precision? It is here, solidly in the second level of machine-like fit, above rough dressed masonry, but nowhere near modern ground or lapped finishes. Remember, Petrie did not have access to modern GD&T or geometric dimensioning and tolerancing for flat tolerance. There was no grid probing, no interferometry, and no uncertainty budget. However, from a basic engineering perspective, this is what Petrie is saying in simple terms. The creators of this sarcophagus achieved high straightness, that is, edges close to a true line. The faces were nearly planar, with only slight convexity. The magnitude of the curvature differences between faces, hollow versus bulge, implies they weren't chasing a mathematically perfect plane everywhere. They were producing functional, extremely true surfaces with the tools and checks that they had. What would happen to these numbers if we measured them today? And perhaps we have, I just don't see them published anywhere. Petrie's measurements would almost certainly appear worse if they're redone with modern instruments, but not because the object is less precise, but because the measurement itself would be more revealing. Petrie was measuring large-scale straightness, overall geometry, not the fine microtopography of the surface. He reported mean or best fit deviations rather than peak to valley extremes, which means localized high and low spots were effectively averaged out by his methods. We would still have the same object being measured, but with a more realistic view of the variations. Compare this sarcophagus for a moment to one found in the outer part of the pyramid complex, also of granite, in tomb 621. The errors on this one are far greater, in the hundredths of an inch this time versus thousandths of an inch. Still amazing work, but the hesitant, caveated descriptions Petrie gives it are in stark contrast to the unabashed praise he gives the main one. With this data in mind, I want to show you how, in some practical ways, this extremely good level of accuracy could have been achieved using clever methods and tools perfectly within the grasp of ancient Egyptians. Once again, the question is this: how do you get something flat when you don't have anything around you that is truly flat? Everywhere around us, we have items that look flat, but they really aren't. Everything we see in our house that is considered flat, other than glass surfaces or perhaps your marble countertop, is probably not even remotely flat beyond that rough level. However, we still call it flat. No, what I'm talking about is how do you get to that machine level of flat for the first time if you have no milling machine, no precision surface grinder, or other such very flat surface? Well, this problem has a very basic but genius solution to it that is still used today. Welcome to the fascinating world of surface plates, something you've probably never heard anyone say. I promise you we will bring this back to ancient Egypt, but in short, we have to understand surface plates before that. A surface plate is a solid flat plate that can be made from metal or stone that is used as the main horizontal reference plane for tooling setup. In other words, it is the key to building all the rest of the precision measurements and tools needed to create other precise parts. But you may ask, if a surface plate is the source of flatness, then how can you make a surface plate itself? Well, oddly, that is the one thing that can be made very flat without advanced tools. Let me introduce you to what is known as the Whitworth three-plate method. I owe a huge thanks to a wonderful book called The Foundations of Mechanical Accuracy by Wayne Moore that describes this process in depth. If you're going to go around saying that everything ancient had to be made with advanced technology, at least read this book first. The three-plate method was officially developed in the 1830s by Joseph Whitworth, but as you see from the process, this was within the skill level of ancient Egyptians, and we do have some evidence to show they knew the basics of this process, and the rest I think we can present as a reasonable hypothesis for them knowing it. Basically, to use the three-plate method, you need three surface plates that are fairly flat. These could be hand-scraped flat, the metal could have been poured liquid into a mold and then let cool flat, it really doesn't matter. But the better those initial plates are to flat, the less work you will have getting it truly flat. Let us take each of these plates and call them red, green, and blue to keep track of what plate we are using at what point. Here is an exaggerated side view of what it would look like at step 1. Hopefully the plate would start much flatter than this, but this is to show you the general idea of what's happening. In step 1, the red and green plates are lapped or rubbed together in alternating manners. That is, one plate remains stationary while the other is rubbed against it, and then the opposite plate is rubbed against it. At the completion of this step, the red and green plates agree with each other, but that is all. In step 2, the red plate acts as the control. It remains stationary, while the blue plate is rubbed against it. At the end of this step, both the green and the blue plates have picked up the error from the red plate. They do not agree with each other, however. Next, in step 3, the green and blue plates are lapped against each other in an alternating manner. Since both of these plates picked up the error of the red plate from the previous 2 steps, lapping them together removes some of the error from the red plate, bringing them closer to flat. In step 4, the green plate acts as the control, and the red plate is lapped against it. At the completion of this step, all 3 plates are of roughly equal flatness, but one, green, is convex, and the other 2 are concave. Next, in step 5, we move back to an alternating pattern and lap the 2 concave plates against each other. This results in 2 fairly flat plates. At this point, only the green plate needs to be brought up to the same level of flatness as the other 2. Finally, in step 6, the single convex plate is lapped against the blue control plate. The result is 3 plates that are in agreement with each other. It is worth noting, although this yields great precision from nothing, Joseph Whitworth later improved on the technique by using engineer's bluing and hand scraping as previously mentioned. Engineer's blue alone was an improvement over using no indicator. With the blue, it is easy to see which areas have and haven't been scraped. So how does this relate to ancient Egypt? Let's go back to those casing stones. We know from examples on existing stones where we found it that the Egyptians used red ochre for testing their work. It is found smeared over many surfaces as marking lines and in other places. This is analogous to the use of engineer's blue on a surface to see what part is rubbed off and what part remains. That red ochre would have shown the high and the low spots. I believe it is within the skills of ancient Egyptians to have used a 3-plate method variation to get a very flat surface plate for testing joints. However, where the ancient method would have to be different, the surface of the casing stone, statue, sarcophagus, or stele would have served as one of the plates being cycled through the whole process of being rubbed together as we went through. The method would have to be modified somewhat because the plates would be the only possible moving portion, unlike the Whitworth method, where at some point each of the 3 plates needed to be immobile while the other 2 were moved. In any case, each set of 2 plates plus the workpiece would need to be rubbed together in alternating steps to make them all more flat. They couldn't have just used all 3 plates at the start, because when the workpiece was introduced into the rotation, it would be very far from flat and mar the known superflat plate. This brings us to what type of plate would need to be used to work such hard stone. Now, the plate could have been made from copper or bronze, and then quartz sand, emery, or corundum grains could have been placed between the plate as a lapping medium. These 3 abrasives are all found in abundance in Egypt in wadi deposits, and they can cut diorite or hard granite. If copper or bronze was used, the grains would embed themselves into the surface and create a tough, flat plate that could grind away the hardest stones in Egypt. Think of this as incredibly heavy-duty sandpaper. We don't look at the paper portion of sandpaper and say, how could paper ever polish this hard block of walnut? No, we are interested in the grit that is glued to the paper's surface that can sand the wood. In the same way, the hard quartz or other abrasive sands of Egypt would work their way into the metal and get stuck there, and more sand could be added until the correct amount of abrasive was found. This was a learned skill, an art as much as a science. As the plate and work surfaces grew closer to truly flat, water or oil could be added to create a slurry. This fine slurry of sand and water would induce a high polar mirror finish, exactly like we see on the highly polished stones in Egypt today. That process could be used with granite or diorite plates instead of copper or bronze. However, I personally think that the softer metal would actually work better due to the first layer of abrasive sand being able to embed in its surface. Sure, it's much faster to use a modern industrial diamond saw and then a buffing wheel with abrasive, but it's going to have a similar result using this ancient low-tech method. Nothing crazy, no space-age technology, you just have to know what you're doing. This is, I believe, how the ancient Egyptians achieved that nice flat surface that they did on some sarcophagi. The variations in quality between boxes show it wasn't a refined industrial process, but rather an art and a craft that was being developed with trial and error. Does the water mixed with emery work better on red granite with a copper slab? Does quartz sand mixed with oil work better for diorite with a granite slab? What happens when you rub limestone on limestone, diorite on diorite with oil and corundum? What you are seeing here are the glimmers of an early civilization grappling with the problem of flatness via trial, error, and reason. They didn't have books on machining history like I do. They had to just see what worked and what didn't. When they found something that worked, they repeated it, tried to refine it, and sometimes it worked to spectacular results. In the end, the Egyptians were solidly within the machine tolerance range, but close to the lower limits of that tolerance. It is a total mental cop-out to say, well, it's too advanced, they had lost technology. Instead, we must start with first principles and work from there to figure out how they did it. Claiming everything is a lost advanced technology is the modern equivalent of blaming an evil spirit for the river water making everyone sick. It is an explanation that shuts down further thinking and helps no one. Finally, I know it's going to come up, so I'll just address it now. The topic of super precision stone vases deserves its own investigation, and trust me, it is coming. As always, thank you for watching.